Good morning, good afternoon, and good evening to viewers around the world, and welcome to our third Global Reaxys User Day. My name is Eric Siemens. I lead the Life Sciences team in Europe for Elsevier, and I have the honor of being your host for the first half of the Reaxys. It's great to see you all, our chemistry community, to come together here online. This event is recorded live, and we have some great speakers lined up for you today. All are experts in their field, and they will present a variety of very interesting cases. Now, before we start, I have a few housekeeping topics. First one, yes, we will make recordings available after the event, so you can rewatch or view presentations that you might have missed or share with your colleagues. And then a few things about the webinar format, and I'll show you a slide. To the top right, you can go to full screen view if you like. There's a volume control there. And at the bottom right, you can see the chat function. You can click it and then the chat function opens up. There's a Q&A there. There's a chat there. And please ask your questions at all time. We will make sure that they will be answered. If we cannot answer them live, we will answer them after the event. There's also a full agenda available for you at the top left, so you can see all the sessions that are here today in the AM and in the PM. Now, I want to introduce our first speaker of today, Quentin Perron of Iktos. Quentin is a medicinal chemist by training. He holds a PhD in organometallic chemistry from the University of Geneva, and he held different roles at UCLA and Laboratoire Servier before starting to focus himself on data science and cheminformatics. In 2016, Quentin co-founded Iktos in Paris, and Iktos is a startup drug development company that develops AI technologies for de novo drug design. Quentin serves as their chief science officer. Under his leadership, Iktos has made a market presence, so we're happy to have him here. Dr. Perron will speak about AI in the future of chemistry. Welcome, Quentin. It's over to you.
Thank you, Eric. Thank you, Reaxys. Thank you, Elsevier, for this invitation. I'm very proud and honored to present today Iktos' vision of the future of chemistry. Few words about our company. I'm not alone in this fantastic journey. I have two partners, Yann Gaston-Maté and Nicolas Dohu, experts in the pharma industry, experts in artificial intelligence, and a very strong team with a lot of expertise in medicinal chemistry from different pharmaceutical companies and finance, etc. We are backed up by our investors, Omnes, the Biopharm, and Ventures. Now we have 70 people with a full footprint in Asia, in Japan, in US, and we try to use the best of the science, of the AI in the field of small molecules. So as you know, to discover a new drug, it's quite a complex journey. It's something very difficult, and I think you know this type of chart by heart. And at Iktos, our focus is here. Starting from a target, a biological target, how can we go to a drug candidate as fast as possible? And as you know, it's like solving a Rubik's Cube, trying to fix plenty of different parameters on the same molecules. And to do so, you need to pass by a successive design, make, test, analysis cycle in order to understand what drives the activity, what drives the solubility, what drives the stability, etc., to, at the end of the day, to find the molecules maximizing all your constraints simultaneously. So this is very complex, as I said. It costs a lot. It requires many years and many molecules has to be done. And the success rate is not very high. So the question is how AI can help to that difficult task. So for me, my definition of AI is technology which is able to predict very complex tasks. So I think everybody is aware about ChatGPT and other type of technology like Midjourney, DALL-E. Those technology are able to do some fantastic job, and it's how to predict very complex things going from a text to an image, or here simply asking a question about Iktos and having a quite convincing answer. So everybody knows about ChatGPT, but I think it's important also to understand that this revolution occurs as well in the field of drug discovery, and it's well known from the public. But similar technology has been applied for protein structure prediction using transformer, GNN, but also more all technology like affinity prediction, QSAR models, passing by SVM, deep learning, etc. More recently, massive virtual screening, with the size of the database, which start to increase a lot with billions of compounds. Now you need to apply new techniques, new approach to perform this type of virtual screening. More recently, you have retrosynthesis analysis. During many years, we thought that it was only available for expert chemists, for human brain, but now retrosynthesis is achieving quite impressive results, and I will discuss about that. And also molecule generation. We call that drug design, designing molecules like hearts, like a piece of heart, I would say. But now AI is able to design molecules, and this is more or less the topic of today, retrosynthesis, molecule generation. So it's clear that now AI is bringing new perspective on what to make, and all those technology are fantastic, very impressive, like AlphaGo and this type of technologies. But still, first, it's only starting points. So from there, you need to design molecules, and also you have to make those molecules. Every company, every AI, whatever the magic of the AI, you need to pass by this design, make, test cycle in all cases. So there are plenty of AI, but the problem of today is that the make still looks like this. You have a listing of molecules to make, either designed by AI, either designed by chemists. You need to go to the literature, you need to organize your workload, you need to order the compound, then to set up your experiments, select your material, launch your reaction, monitor the reaction, perform the workup, etc., etc. And then purification. I'm not talking about the analysis and the test, but as you understand, as you know, if you're a chemist, that this is still quite a manual process. So the big question, the elephant in the room here, is how can I go from a listing of molecules, whatever the design, AI, human, to I would say powders ready to be tested. And I want to do that as fast as possible. So at Iktos, we are convinced that the future of chemistry is passing by a new way to go from here to here. And we are not alone. Plenty of companies thinking about that, understand that this is a key element to accelerate drug discovery, to accelerate the discovery of new drug candidates. We have to accelerate the chemistry. And those companies are using different type of approaches, either with AI or without AI. And that makes a big difference. Because if you want to build such a platform, you have different key elements. Again, I have my listing. I need to define for each of those molecules a synthetic pathway. Then I need to order my compounds. I need to, of course, I will resave them, organize them, manage them. Then I need some sort of a robot because I want to automate the things, and then purification analysis to end up to this powder ready to be tested. This looks quite simple, but if you want to have an efficient platform, you will understand that there are some key dependencies needs to be fixed. For instance, synthetic pathway. If I have molecules here designed by my AI, which are not feasible, I don't have any synthetic pathway, I can forget about my platform. If I have an AI which design reasonable molecules, I can find synthetic pathway. But if this synthetic pathway is not compatible with the robots, and the chemistry which is performed on the platform, I can forget about my platform here. So those two dependencies are very, very key for success. So the question we can ask ourselves is, how can I build a system where the AI, the design here is connected to the synthetic pathway and to the robots, and it's basically connected to the make with all the underlying dependencies. And you cannot do that without AI, and I will show you, because there are two main approaches. The first one is, okay, I can use a robot and I don't have AI, but in that case, I am obliged to do library design. I have the same reaction, same exit vector, similar building blocks. Let's say it's the Suzuki coupling on a bromine exit vector. I have a list of boronate, boronic acid, and I will do coupling using a robot. Fine, this is library design. The output is simple molecules, one step only, and you do that on a given series for a given project. This is some sort of automated chemistry. We are targeting a more ambitious vision. We want to do with robot drug design. So we have different reaction, different exit vectors, different building blocks. We want to mimic what chemists are doing in the lab. So for that, you need AI. The output of that is much more complex molecules, because you can do several reactions, several chemistries, so you can build more complex molecules. And you don't care about if it's project 1, 2, or 3. You can run all those projects the same day on the same platform. And this is guided by AI. So this is more an autonomous approach of the automated chemistry. And this is the topic of today through the Iktos robotic platform. And the key element of that is integration. How do I integrate around the robot all the elements of drug design, retrosynthesis, compound ordering, compound management, etc., etc. So this is our platform at Iktos. So basically, we generate molecules using Machia. We identify synthetic pathway using Spire. Then I will show you how we schedule and organize our workload using Elakia, how we run the chemistry into the robot. Right now, we received the robot 1 year ago, so this platform is very young. And the purification analysis and test is performed by external partners, and this is something we will integrate soon. So first, generate. So we have built a very nice platform called Machia, which takes as input plenty of different types of fitness function. Ligand-based 3D information, structure-based 3D information. You can import data, build machine learning models, generate molecules, connect external fitness function you may have using your in-house model, etc., etc. So this AI is fed by different type of fitness function. And we have a unique approach to generate molecules with synthetic feasibility by design. Like a chemist, Machia generates molecules by leveraging commercial building blocks and synthetic transformation. I will show you, it's very simple to understand that. We have one AI which make prediction amongst 1 million building blocks. This AI tries to predict which building blocks can react, and you have an array of different probabilities, different building blocks. So let's say that the first building block is this one. Then we have a second AI which predicts reaction. We have 2,000 name reaction, basically all the reaction you can find into the patent. And based on these building blocks, this AI predicts which chemistry can be done on that. The top probabilities here, it's bulk removal. So now I have this virtual intermediate, and the first AI will try to predict, based on this output, a new building blocks which can react in this position. Now the best probability is this building block. And starting from those two virtual compounds, the second AI try to predict again, what can I do with those two building blocks? Which type of chemistry can I operate here? And this is amide formation to finally obtain this one. And the system can do that up to several steps to build virtual molecules. Those two AI communicate together to generate 1,000 molecules per steps. And those molecules, those 1,000 molecules, are scored again, different type of scores. 3D, QSAR, descriptors, presence, absence of substructures. We obtain a maximum score for the given batch. and we send back this information using reinforcement learning. We're going to update the weight of the reaction prediction, the commercial building blocks, to generate 1,000 molecule again. And step after step, using reinforcement learning, we maximize the given fitness function. And thanks to this AI, contrary to other approach where they have plenty of AI to do plenty of different type of job, here we have only one AI which can do all the chemistry published in the patent. We can grow, we can link, cyclize, heterocyclization, macrocyclization. And if you do the math, 1 million building blocks, 4 steps, and 2,000 name reaction, we cover a very huge chemical space, 10 to the power of 27, with high diversity and novelty. So the output of Micah is a listing of molecules. For each of those molecules, you can see the decision taken by Micah to generate these final molecules. And of course, we have the structure-based information score. So now we have this listing of molecules. We need to identify a synthetic pathway. For that, we have designed SPIA, trained on the literatures. Right now, this is the public version of SPIA. It's Pistachio database. And we have something like 5 million reaction. And we use this in our robotic platform. We have different type of interface, SPIA API to be connected to external system like generative AI to triage millions of molecules, and also SPIA GUI with the interface. So I have my list of molecules from Micah. Then it goes to SPIA API, and SPIA try to identify for each of molecules different type of routes. And I have a list of routes for each molecules. Now the question is, which route should I take? And for that, I will use Ilaka, the scheduling platform. So again, a list of molecules, plenty of routes per molecules. And then Ilaka say, okay, in order to optimize the robot capacity, I will do batching. And I will try to select some routes which are good to be batched together. Okay, so for instance, I will select the route 4, here the route X, and here the route Y, and together it seems to be the best combination to use the robot at its maximum capacity. And then we send back that to the chemist for validation. So we expose to the chemist the outputs of the Ilaka decision, and the chemist can decide to order the building blocks, and the reaction are placed in queue. Then the synthesis. So we're going to send all this information to the robots. Our robotic platform is a ChemSpeed. It's a very small robot, 2 meters, 1.5 per 1.5 meter. So it's a small footprint. It's very reliable. We have been able to design all the components to be compatible with our workflow, and you can run 100 reactions per day. So the setup is the following. You can do basically what any action you need to do in a classic, I would say, chemistry lab. You can all move vials, read barcode, database operation. You can dispense solid, liquid, heat, stir, filtrate, evaporate, etc., etc. So here we have solvents. Solvent is added to the starting material. Then the starting material are mixed into the reactor. When the reaction is over, it goes to support phase extraction, workup, and then evaporation of the solvent. We had to develop our own chemistry because, of course, we have used AI to transform procedures to a structured database with solvent, catalyst, etc. But the problem of that is the chemistry which is published is not necessarily compatible with the robots. So we had to develop our own chemistry to avoid very low temperatures, reactive starting material, reaction which generate different type of radioisomer, hygroscopic starting material, etc., etc. So based on literatures, based on expertise from our chemists, we have developed our own chemistry. We have also developed new support phase chemistry compatible with the robots. Some example here, we now master 14M reaction, which covers something like 37% of the patented literatures. We have more or less most of the coupling proposition, protection, deprotection, amine reactivity, etc. and with a reasonable success rate. Then once I want to run a campaign, I have different type of project 1, 2, 3, different type of exit vector, different type of chemistry. And I want to do that on the same day, on the same robot. So again, those listing of molecules are going to Spire, which generate different type of routes. Then Ilaka picks the best routes, to optimize the position into the robot. And this is what we can obtain here. First reactor, we have the 10 Bromo-Suzuki coupling, the Bromo-Bergvall coupling here, and then SN2 alkylation here. And Ilaka decided to select those routes to make those molecules because they can be batched on the same reactor on the same day because they share more or less the same temperature and the same duration. And this is for the reactor 2, different type of chemistry, different type of condition. And this is how Ilaka organize the workload. And then we are in the lab. Ilaka has organized a workload. The compound has been ordered to external providers, and those reactions are then sent to the database. Oh, this video should work. I don't know, my network is not very high. I hope I don't have any issue with internet. And then those compounds here, those compounds are those information coming from Ilaka is then added to this database, and this database here is read by the ChemSpeed. The ChemSpeed executes the chemistry and then send back this information to this database, which is then read by Ilaka. So there is a communication between the ChemSpeed, Ilaka, and this database here, and we store this information once done into Dotmatics, our ELN platform. So DMT cycle at Iktos right now. So as I said, we received the robot 1 year ago. So after 1 year, we have installed the robot, we have developed our chemistry, and we have started using this robot. We have completed 6 DMT cycle, run 1,200 reaction, 14 M reaction, 150 pure compound synthesized and tested. And basically, it takes something like 2 months with a 60% success rate as in average. 1 week to design molecule in Ilaka, 1 to 2 weeks to have the retrosynthesis, order the starting material, receive the starting material, 1 to 2 weeks to do the chemistry, 1 to 2 weeks for purification, and then biological assay. We are using this platform to run our in-house pipeline on different type of targets. So as you understand, retrosynthesis is a key component and a key element of our vision of the future of the chemistry, the AI in chemistry. And having made this, having understanding that at Iktos since our inception, we decided to team up with Elsevier because we thought that mixing the best database of the world, the high quality data Reaxys has with reaction and the best AI we have been able to design over the year, we thought that there is an opportunity here to design the best retrosynthesis technology of the market. Of course, we will not stop here. We think about using developing more features, more options, more interface like synthetic accessibility score through an API. We are working on how to do forward reaction prediction, how to predict reaction condition. Of course, Elsevier are sit on a huge database of ANME data. So we are also thinking about how to use this data to make ADMET prediction, etc., etc. So we are more than happy to have concluded this partnership, and the future is bright. And I hope we will be able to organize more sessions like this one in the futures on new tech we are co-developing. So I want to thank the Iktos team, composed of talented researchers in cloud computing, AI, machine learning, chemistry, development, etc. And I want to thank you, and very happy to take questions today.
Thank you very much, Quentin. This was really interesting. I have a question for you for the end, but let's start with a few questions from the audience. and there's quite a few coming in. One question I can see is, what are the parameters considered by Ilaka to choose the best route generated by SPIA?
Yeah, that's a good question. So right now we decided to, the fact we are limited by the fact that the reaction is run on reactors, and reactors is composed of 48 vials. So we are more or less limited by the fact that they are all at the same temperatures. We cannot eat each vial independently. And you're limited by the fact that you need to consider the reaction having the same duration. So right now we batch chemistry given the temperatures and the duration. That's it. We have two reactors, so we can do different type of parameters.
Yeah. Another question, and I need to interpret it slightly, but I think the question is, do you sometimes meet a situation in which the structure chemically makes sense coming out of the model, but then when it's performed by the robot, it turns out to not make sense?
So yes, you mean that it's run by the robot, but at the end of the day, we don't have the expected compound, right? The chemistry did not happen. So yeah, that's a good point. That's why at the end of the robot, it follows, I would say the classic process. It goes to purification, analysis, and test. Test only if obviously the analysis is conclusive. If after the analysis, the compounds come back and it's not the structures designed by the system, we have this feedback loop, and we have this information, and we can report that as any chemist would do in the ELN. The contrary here, compared to classic approach, is that it's automated. So it goes back to the ELN. We don't have the expected structures, and then the medchem will take decision based on that. Either he believes that it's still an interesting molecule, let's test it, or it's not happy with it, and he will launch and trigger again the robot, either by modifying the setup, the chemistry, changing some parameters, or maybe in order to not lose time, take these compounds and make it done by an external provider because maybe it's not compatible in the robot.
Yeah. And does that data that you feed into the ELN, also the negative data then, does that also get used to retrain the models at some point?
Yeah, for sure. It's a very good point. Right now, we again, the platform is very young. We have launched thousands of reactions, but not hundreds of thousands. But yes, it's in our plan to monitor everything, because like the chemist action, when we display to the chemist the route selected by Ilaka, the chemist dislike, all this information is very precious, and we keep this information for the futures. The same for the purification. Once we will integrate purification into this loop, we'll be able to understand which column, which condition, for the futures, to be able to predict which column, which condition, which analysis to perform, which chemistry to run in such and such context. Because our vision is really to build an autonomous platform in the future, so all expert decisions taken today will be taken in the futures using AI.
Yeah. And I think I heard you say that you have 48 vials. How many? There's a question: how many reactions you can perform in parallel on your platform?
Yeah, so we have 48 vials per reactor. So we have 2 reactors, so it's 96 reaction we can operate per day.
Would you say, another question from the audience, would you say that the use of the robot makes the chemistry greener or more sustainable in a sense?
Yes, for different type of reasons. First, using AI and the way we sample the chemical space and we do the chemistry, we converge faster. So we do less molecules. Second, we do very tiny amount of molecules inside the robot. So very small number of solvents, etc. Yeah. So we believe it's greener, but still we order building blocks, which are sometimes advanced building blocks, which are done to external providers. We ship them, etc., etc. So anyway, drug design, medicinal chemistry, it's not very green. It has some footprint because it requires many types of solvent, chemistry, transition metal, etc. But still, by converging faster using AI, we can reduce the number of molecules to make, and at the end of the day, find drug faster and spend less money, less time. So maybe a lower carbon footprint.
Yeah. Someone asks, what is the accuracy of Machia? How do you measure the accuracy? And does it cover existing routes and new predictive routes?
Yeah, that's a very good point. We are right now doing some, of course, we are doing chemistry for our pipeline, but we are also working in publishing some results on a proof of concept. Right now, what we observe is going from Machia to ELACA. We have 80% of the molecules designed by the system doable by the robot. So 20% is done externally to external CROs. 80% can be done in the robots. And then from the robots to the porter, 80% again. So 80 by 80, it's something like 60% at the end of the day, which arrive and ready to be tested. So this is only the beginning of the platform. Again, we believe it's quite an interesting results. And our philosophy is not to do, I want to make this compound and I will put all the effort to make that compound. With the platform is, I want to populate this chemical space. So I want to do 20, 30 compounds in this chemical space. If I do only 15, that's fine. You know, I catch data. If the AI is coming back again with the same ideas, okay, maybe I need to find this compound which fell at the first round. I will either modify things on the platform or maybe externalize these molecules to an external CROs. But our philosophy to progress the project is a bit different to the classic approach.
Yeah. Another question, does the robot system help with purification?
Right now, as I say, no, the purification is done externally to external providers. Purification analysis and test is done externally. And this is plan of our Series B. We are starting our Series B right now. It's to enhance the capacity of this platform, integrating purification, analysis, and early admin around the same robots.
Yeah. Now, you mentioned that chemists assess the priority compounds coming out of ELACA, right?
Yeah.
And your talk was around the future of chemistry. What are your thoughts around the future for chemists in this future for chemistry, especially when you are working towards an autonomous platform?
Yeah, so I think we need experts. You know, it's still a chemist who is behind Machia saying, okay, inside this pocket, I want to make this P stacking interaction. I want to interact with this and this amino acid because compared to what I know, my knowledge, etc., I believe it's very important. So the chemist set up condition for the AI to generate interesting molecules. It's like ChatGPT. If you ask dummy question, you will have dummy answers. So here it's the same. If you set up the platform properly, you design very nice molecules, then the AI trying to find some routes and organize the workload based on the optimization of the platform. But maybe at some point the chemist can say, oh no, okay, it's good for the optimization of the platform, but here I disagree with this reaction. I dislike this, and the AI needs to review its strategy. And so I believe we need experts. Then we need biologists. We need to analyze the output of that. We need to take decision to understand the structure-activity relationship. So for me, the future of the AI is like a pilot in an Airbus. 90% of the flight is using autopilot, but still you have to take off, you have to land, you have to take decision given the weather forecast or the environment, and the same here. So I see the chemists behind Machia, Spaya, ELACA, maybe doing less bench chemistry, more piloting the system and reading the literatures, etc., etc.
Yeah, clear. Yeah, and I think I remember someone saying that chemists that use AI will be heading over chemists that don't use AI. One question, I think from someone in a university who asks, can the robot be operated by a PhD student? So I guess how technical does your expertise need to be to also operate the platform, the system?
Yeah, that's very good. So ChemSpeed is a very complex software. It comes with AutoSuite, and you can do everything on it. Define any position, millimeters, volumes, etc. So it's very, very expert-based system. And we didn't want it to have that for our chemists, because chemists speak chemistry. A plus B through Suzuki coupling gives C. I don't care about the position of the needle. I don't care about the position of the polders, etc. I just want to put my starting material into the system and then press and play. So Ilaka is not only a scheduling technology, but it's also a user interface where you can perform the platform, use the platform using HT, so high throughput experiments, modifying all the parameters, but also use the platform as a production platform, do different type of chemistry. It's very simple, you drag and drop, you select the temperatures. So I didn't have time today to show you that. We have done other webinars where we present into detail Ilaka, but this was really the goal of this platform, to have very unique and simple user interface. Because if you train a very strong chemist to operate the platform, to run AutoSuite, once he left the company, you have a robot and no one can use it anymore. And we don't want to have
that. Yeah. To that point, someone asks, as today's world becomes more technology driven, especially with the rise of AI, how would you advise undergraduate students studying chemistry to prepare themselves for this shift? As a current chemistry undergraduate, I'm curious regarding the changes in the field. What would be some important skill sets in this new age? And I guess the question extends also to people that are already working in the field, and you yourself as a medicinal chemist at some point focused more of your attention into data science and cheminformatics. So what are your thoughts around that? What are the capabilities that people maybe at university or already in corporate settings need to learn?
So a few years ago, I would say start learning to code. And but I think with the new AI, forget about it. Now the AI is producing code by itself. And I think in the futures, you will have plenty of very nice user interface. And you don't need to code to use an autonomous car. So I think what you need to train yourself is to understand the AI ecosystem, the AI capabilities in different type of the field, to be able to use AI in a very smart way, not thinking that AI will replace you, but to see AI as a very powerful tool and how you can use it as a human expert. I will use this AI to do that, this one to do that, and to build an ecosystem where AI serve you and do not replace you, and to know how to use this, to understand this ecosystem, to understand the AI capabilities, and not to see AI like something strange, far away from you, maybe something which frightens you. It's better to see as a friend, and for that you need to understand how it works to use it the best way. So be curious and read papers to understand the capabilities, and follow the companies developing nice things with those AI, because they will be able to put in your hands in the futures fantastic tools.
Yeah, I think that's great advice. We are approaching the end of our time. Let me just go through the questions to see if there's one final one that I can ask you. And there was one in the list just now that seems to have moved away. I think there was a question around flow chemistry. So is your robot, are you moving towards a flow chemistry type of setup?
No, this was a tough decision at the beginning, because we saw flow everywhere, and we say, okay, should we move forward in this direction? But flow chemistry is something very nice in my view, to do the same molecule every day, and very dangerous procedures, because it's tiny amounts, it's continuous, it's very nice. But to do a very complex and different chemistry with palladium, iridium, different type of transition metal, you are more agile using classic chemistry, classic batch chemistry. We didn't want it to put all the difficulties on the same platform, playing with flow, with tiny pipe, different new and chemistry. It was too complex for us to move into this direction. Maybe in the futures, with a very complex flow decision setup with triage, different type of reaction, etc. But we believe it's simpler to order the starting material as we order, mix it, filter. But yeah, maybe we'll change the future.
Wonderful. Thank you so much, Quentin. This was a hugely interesting presentation, and I see a lot of questions come in that we've and we've been able to cover many of them. So thank you very much for coming here and being our keynote speaker. The platform will move the people that are viewing this session also to the next session, which is going to be interesting as well. Thanks very much, Quentin, and until next time. Bye-bye.